Welcome back, everybody. Let's take a look at two populations, but this time we're going to be interested in something that is quantitative from those two populations. So therefore, we have two cases here. We could be asking a question regarding the means or the standard deviation. All right, so let's go ahead and take a look at this little schematic that we observe. We see here at the very top that we have something called smoking. That's my random variable X, and that's yes or no. So this is qualitative. And this is called a factor. So anytime you have a population and you're going to go ahead and essentially sort your population by something that's qualitative, that's a factor. This case, the factor is smoking status. This is either yes or it is no. Now, this is actually pretty concerning because we see here that when you take a look at the left-hand side, we see that it says Pop 1 is pregnant women who smoke, and Prop 2 is pregnant women who don't smoke. So it looks like my population was all pregnant women, and we can see that we are separating all pregnant women by smoking status. Now, from those two groups, we clearly have a population. We can see that we're going to be interested, I guess, in the length. It could be the length of pregnancy or length of the baby, or length of any other trait related to their pregnancy. So if we were to look at the entire population, we have the blue group, which is all possible pregnant women who smoke. On the right-hand side, we have all pregnant women here who don't smoke. So if I was interested in that variable, right? So let's go ahead and write out the variable. What are the variables that we're interested in? We're interested in the length of pregnancy for women who do not smoke. And then we're going to look at the length of the pregnancy for the women who smoke, so with smoking. And clearly, these parameters are out of our hands. So those are the parameters right here, mu1, the average, right, the mean length of the pregnancy with smoke, and then the mean length of pregnancy without smoke. So because I don't have access to this, obviously, I'm going to go ahead and sample. And that's what we observe happening right here. So this would be your sample. This right here would be your sample. And so the logic is actually pretty amazing because we're going to say pretend, right? The null hypothesis is the hypothesis of no change. Pretend that there is no change. There's no difference between the length of the pregnancy for women who smoke and then the length of the pregnancy for women who do smoke. Pretend that there is no difference, and therefore we're saying that mu1 is the same as mu2. So this would be this is mu2 without, and then with is mu1. So if mu1 is equal to mu2, then if I subtract these, mu1 minus mu2, I get 0. And so because I don't have access to the population, I'm first going to go ahead and collect a sample from each population. So let's collect a sample per population and find the corresponding mean. So if this is your sample, we can from there go ahead and take a look at x1 bar. And we can go ahead and take a look at x2 bar. And now that I have my sample evidence, I'm going to say, if I subtract them, is that statistic close to 0? So is there difference close to 0? Obviously, in order to answer this question, you need to know the sampling distribution of this random variable. So we will get different differences if I repeat this procedure over and over again. And that's what we saw when we moved away from probability to looking at distributions. So lucky for us, everything that we've seen in the past still holds. So we actually do know what the sampling distribution of x1 bar minus x2 bar is. So that's the difference of the means. So if we assume we have big enough sample sizes, so that's a strong assumption here, or the populations are normal, then the sampling distribution of the difference of the sample means will have a center of, you would never believe this, mu1 minus mu2. And so this, again, should remind you a lot of when we did mu of x bar was simply equal to mu. In other words, the population mean. So look at the similarities there. Then in the standard deviation, so the standard error of the sample mean was sigma over square root of n. Now, this is equivalent to the following: sigma squared over n square root. So if you do a little bit of math, you'll see that that's what we get there. Now, the standard error for the difference is actually known, and it's given by the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So again, look at the similarities between what we have now and what we had a couple units ago. The last thing is that the central limit theorem says not only do I know the center and spread, the standard error, I also know that the difference will be approximately normal. And so we've seen this before. There is one big problem. These formulas assume that we have the population standard deviation. So I know the population standard deviation for group 1, in other words, the pregnant women who smoke, and I know the standard deviation of group 2, the pregnant women who don't smoke. But unfortunately, I don't even know the center of these populations. That was the whole question that I was trying to answer. What is the center? What does their mean? And in order to compute the standard deviation, you need to know what the mean is. So because we don't know what the mean is, right, that was the whole goal of this, like let's take a sample and examine it, I can't actually tell you what the standard deviation is. So for most realistic problems, this is going to be one of the only things that we study in detail. For most realistic problems, you do not know the standard deviation, either from group 1 or from group 2. So this result actually has a strong limitation in that this isn't very helpful. Now, we're going to go ahead and just simply replace this with S. So we essentially say, well, what happens if you don't know sigma? We could try and use S, kind of like how we did before, but that would be a different distribution. And unfortunately, there is no known statistic. There's no known way to combine x1 bar minus x2 bar with S1 and S2, sample standard deviation, to know the exact distribution. So this is actually one of the few open problems in statistics. It's known as the Behrens-Fisher problem. And it's still open. So if you really are curious about this, you can also do some research as to what kind of statistic can be made when the when the population standard deviations is unknown. And there's all kinds of different statistics. There's one major approximation. So even though there's no way for us to know exactly what the distribution is, there is one major approximation that is used, very popular, and this is called the Aspin-Welsh t-test. Look at how similar this is. This is x1 bar minus x2 bar. So this is our So this is our sample difference, sample stat, and then mu1 minus mu2, that's the hypothesized value. Which mu1 minus mu2 is assumed to be 0 right now, so that could go away. And then at the bottom, we see S1 squared over N1 squared plus S2 squared over N2 squared. And notice that that's essentially what happens if you replace sigma right here with S. So this was very logical. It's one of those very first statistics that was presented. This was actually presented in 1938. It was proven by the statistician Welsh. And he proved that this is approximately normal with this very strange computation for degrees of freedom, where you have to round down to the nearest whole number. And he proved in that paper in 1938 that this statistic does in fact follow a approximately follow a t distribution with this many degrees of freedom. So that's what we're going to end up using, because it's very natural to what we did before with the t distribution, when we first introduced the t distribution. Okay, so our takeaway is the following, and that's pretty much it. Now that you got the t statistic, you can perform a test. So let's go ahead and summarize what it is that we'll be doing. When you're asked to determine whether there is a difference between two population means, you're going to determine the parameters. Remember, the parameters are always the what is mu1 going to be equal to? So it'll be the true mean of something. And then you're going to go ahead and write out mu2. So you need to know what the population there is as well. Mean with some trait or characteristic that you're interested in, that you're going to go ahead and measure. The hypothesis will always be that mu1 is the same as mu2, and the alternative, well, that is up to you. Depends on what it is that you're trying to show. And that's equivalent to the way that we're going to see it in StatCrunch of mu1 minus mu2 being 0. So we basically just move everything to one side. And the alternative, that mu1 minus mu2, throw in your comparison here, and then 0. You need to check the conditions for the sampling distribution. So up here, if you remember, we said that the central limit there requires that N1 and N2 be large enough, or the population separately be normal. So you're going to have to go ahead and take a look at POP1 and just run through the checks. Obviously, these hold SRS independence. But then you're going to have to check the shape requirement, which is that sample size number 1 is greater than 30, or the random variable that this comes from, x1, is approximately normal. And we can do that with QQ-plot and box plot if we have data. You'll do the same thing with POP2. Do the same thing for shape. And we're going to go ahead and say that the second sample size needs to be greater than or equal to 30, or the second random variable, there's evidence that that population is normal. The command is very simple for our test statistics. We are clearly going to do a t-stat when we're sketching it. Something worthwhile to note is that we will not be computing this by hand. You have technology for that. So whenever we sketch this by hand, we're going to use the smaller of the sample sizes. So we're going to use the smaller of sample size 1 or sample size 2 to compute our degrees of freedom. This results in a more conservative approach, but is still most likely, when we carry this out, we really won't notice much of a difference. It's just an approximation so that we don't have to sit here and compute this degrees of freedom every single time. The test statistic, the command, it's exactly the same as before. It'll be stats, t-stats, but now with 2 samples. And that's pretty much it. All right, so this is the framework of the hypothesis test between 2 population means. In the next video, we will go ahead and actually carry out this test.